We looked at a couple of them. We're taking them one after the other now so that we have deeper insight about them. Just to refresh our memory, we mentioned the importance of understanding the mechanisms of toxicity. Mind you, we are talking about toxicity of these chemicals. So when you say importance of understanding mechanisms of toxicity, it is the chemicals that are toxic, and we want to understand. It is good that we understand their mechanisms. And when we understand the mechanisms, how does it help us? It helps us to estimate the possible harmful effects of the chemicals. It also helps us to establish procedures that can prevent or antagonize their toxic effects. It also helps in designing drugs because these chemicals, they act in a particular way. And if you are able to understand their mode of action, then you should be able to design drugs in such a way that they can, bring about reduced effect, so to speak, even when they affect us. When we understand the mechanisms, it also serves as a basis or the basis for therapy upon overexposure. It enables further understanding of some of the biological processes that are involved. So that is just to refresh us. And we said that these mechanisms are in 4 steps. The first step is delivery. So the product or the chemical must be delivered onto a particular site, onto the target before it can act. If you do not come in contact with it, there's no way it can react or cause injury, and so on and so forth. So the first point is that the chemical has to be delivered. So when it delivers on the site of exposure, then it reacts, all right, and so on and so forth. So we tried to look at delivery yesterday. I would say delivery is a movement of the toxicant or the chemical from the site of exposure to the site in which it is its target or site of action. And we also mentioned that it could be the liver. If the drug is delivered onto the liver, that becomes the site of action, for instance, or a kidney, or any other organ in the system. We also mentioned that intensity of a toxic effect depends on the concentration. So it has to do with how much of it that is deposited in the system and whether it is possible to stay for a long time or short time. That is persistence. So if it can persist onto that site, then there is that possibility that it can begin to cause injury. But if it will not stay for a reasonable time, then there's that possibility that the effect might be minimal, so to speak. And then we talked about ultimate toxicant. I would say ultimate toxicant is a chemical that reacts with the endogenous target molecule. Okay, that chemical that reacts with that target molecule, like receptors, enzymes, DNA, protein, lipid, or is capable of causing or altering the biological environment, okay, to become something else, so that it can afflict injury, so to speak. So we looked at factors that affect delivery. We looked at absorption, distribution towards the target, reabsorption, toxication, elimination. Distribution away from me, excretion, detoxification. We continue to look at, and we were reaction. That is what we're talking about here. So this reaction usually lead to injury, because there's no way a toxic chemical will come in contact with a target molecule and not cause injury. It is not common. So this reaction leads to injury to the target molecule itself, the cell organelles, the cells, the tissues, organs, and even the whole organisms. So if one organ is affected, you know that the body system is interconnected. It might not just be the kidney. If it targets the kidney, it is possible that when the kidney begins to deteriorate, other organs too may be affected. So that is why I say this reaction leads to the injury to the target molecule itself. All right? As the cell, organelles, cells, cell organelles, cells, tissues, and organs in that order. You know, cell is the smallest unit of organic, of organism. So it can attack the cell, attack the tissue, then the organ, and even the whole organism may be affected by that reaction. So the reaction of the ultimate toxicant with the target molecule is affected by a number of factors. Okay? And we have mentioned one, the character of the target molecule. The character of the target molecule is very important. If someone comes to you to attack you, it depends on who you are, all right? Depends on who you are, that he might be able to get you or not. So if you are good in resisting attack, then you might go with minimal injury. But if you are the type that cannot, react or act, okay, it will be very bad. So the character of the target molecule, that's the molecule in which the chemical is coming to attack, okay, depends on the character. So the most common targets are the macromolecules, such as proteins, okay, and lipids, and so on and so forth. So the most common targets are macromolecules, such as nucleic acids, proteins, all right? Among small molecules, membrane lipids are frequently involved. Then the types of reactions between ultimate toxicant and target molecule. Okay, so how do they get to the molecule? They bind. Is by binding themselves together, right, with the target molecule, and they do that by altering the hydrogen removal, electron transfer, or the enzymes. Okay, so types of reactions between ultimate toxicant and target molecules. One, they bind to the target molecule, they alter it. Okay, they alter it by hydrogen removal, electron transfer, or enzymatically, right? So we have effects of toxicants on the target molecule. A number of effects, reactions, or reaction of the ultimate toxicant with endogenous molecules may cause dysfunction or destruction. Yeah, because that is the target, that is the aim. It's this, to destroy completely, destroy the proteins, destroy DNA, and so on and so forth. In the case of proteins, it may render them foreign. That is an antigen to the immune system. It will cause it to become a foreign material or a foreign body, okay, to the immune system. So it weakens the immune system completely. So these are very familiar explanations. Then you have the step 3, which has to do with the dysfunction and resultant toxicities. Like we said, once the reaction takes place, the next thing that follows is what? Is injury. So the third step is like injury, the toxicity that happens itself, the toxicity that takes place in that organ is what we are referring to as, step 3. It will cause cellular dysfunction and the respective toxicities. They manifest in different forms, manifest in different ways, right? So the reaction of toxicants with the target molecule may result in impaired cellular function, okay? It will result in impaired cellular function. Normally, each cell has defined programs. So it will alter the program, alter the function of that cell, so to speak. Normally, each cell has defined programs. Programs determine the destiny of cells. That is what we are told. Determine the destiny of cells. That is whether they undergo division, differentiations, okay, produce protein or specialized functions, and so on and so forth. So it will alter that process. Programs control the activity of differentiated cells, determining whether they secrete more or less of a substance, whether they contract or relax, and whether they transport and metabolize nutrients at higher or lower rate. So that will be affected. Okay? Because if it is to secrete, or if the function is for it to secrete maybe nutrient in a particular way, and in the process that the chemical now reacts with the organ, or so to speak, or maybe the protein or the enzyme. The enzyme may be affected. Maybe instead of secreting the substance that it ought to have secreted, maybe in a controlled or in a proper manner, it might be faster than is expected, or it may secrete it more slower, right? Changing its original function or way of operation. So step 4, after the injury is caused, step 4 has to do with repair or disrepair. Many toxicants alter micromolecules, which, if not repaired, they cause damage at higher levels in the organism, and so the organism tries to repair. So when this reaction takes place, the organism fights back. There's nobody that someone will come to attack you, and then I'm very sure that you just sit there for the person to do whatever he or she wants to do to you. There will be some form of resistance. And if you are able to resist in a much stronger way than the person, then he or she may not cause that injury to you. So the organisms, they try to see how they could, repair the damaged molecule or cell or tissue, and so on and so forth. Okay, that is where you have repair. So we are told that the molecular the repair can be done in a number of ways. For instance, molecular repair, we are told that damaged molecules may be repaired in different ways. So this may be done in different ways. One is chemical alteration, such as oxidation of protein, thiols, are simply reversed. So instead of oxidation of protein to thiols, okay, which are harmful to the body, there might be no oxidation of such. Okay, there may be hydrolytic removal of the molecules damaged unit and insertion of a newly synthesized unit, often occur with chemically altered DNA, or it is possible that there will be resynthesis of the damaged molecule. So after the injury, there is repair. And where it is not possible to repair, then you have what is called disrepair. At that point, there's nothing you can do. So at the cell level or at the cellular level, repair or damage cells is not a widely applied strategy in common cellular injuries. In most tissues, injured cells die. In most cases, they die. We're told that an exception is nerve tissues, because mature neurons have lost their ability to multiply. So at that point, there's no way you can have repair. So in peripheral neurons, which blah, 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 these are medical terms. Then you have tissue repair. Of course, in tissue with cells capable of multiplying damage or multiplying. Damage is reversed here through regeneration of the tissue. So the damaged cells are eliminated by a process called apoptosis or necrosis. So the whole idea here is for you to know that, one, for the chemical to be able to carry out its damaging effect, it must be delivered. After delivery, it reacts. After reaction, it causes injury. And after injury, there is possibility of repair. And where repair is not possible, then there is what? Disrepair. That is what we are trying to explain here. Okay? So disrepair has to do with failure of repair. And this may occur due to a number of reasons. One, rate of damage is more than repair. So if the rate at which the organism is capable of repairing, if the rate at which the damage is more than the repair, then at that point, there's no way it can happen, because you're having more damage than than repair. Another one is exhaustion of repair mechanisms. So there could be some mechanisms that enhance repair. And if those mechanisms become exhausted, it becomes difficult for repair. An injury of the repair process itself, such as blockage of some of those processes that lead to repair. If it is blocked, it is no way that repair can take place. So any question or contribution at this point? If there is any question or contribution at this point, you can let us know. We are on mechanisms of toxicants, how they affect the target organs and so on. Hello, are you with me? Hello? Hello?
We are with you, sir. We are with you.
Okay. That's fine. So any question or addition to what I have said? Sometimes you are explaining, but one is not getting it the way you should get. And sometimes you understand better when you ask questions. Because as teachers or lecturers, sometimes you assume that students should know. So where you don't understand, it's always good that you ask questions. Okay? So do we continue? Okay. Adoga. There's a hand up. Adoga, can you speak? Hello? Hello?
Good morning, bro.
Good morning.
Oh, good morning, bro.
Good morning. Go ahead. Good morning.
Good morning.
Good morning. Morning.
Thank you very much for your. My question is regarding to this toxicity. Just yesterday, accident happened in almost 40%. This is in a mining site. There was a carbon monoxide. About 37 persons. So I want to ask, what could be the level of toxicity that led to that, and how can it be prevented in the future? Thank you, sir.
I didn't get the question, sorry. It was cracking at some point.
Okay,
the network was cracking.
Can you hear me, sir?
Yes, I can hear you now.
Hello, sir.
Yes.
Okay. I said just this morning that there was a poisoning at many sites, carbon poisoning, that led to the death of about 7 persons. So I don't know. Can you tell us more about that? What is the level of toxicity and how can it?
That there was outbreak of something that killed people.
Yes, carbon monoxide poisoning in a mining site in Plateau State.
Okay, Plateau State.
Plateau State, yes, yesterday.
Yesterday.
Okay. Maybe
Yes,
drop it in the chat.
That's serious. I didn't hear that news.
Yes, it happened just yesterday. It was on the news this morning. 37 people had died already, and some are still in the hospital.
Carbon monoxide is very poisonous. Very poisonous. Very, very poisonous. I know. I don't know. Could it be? Um, did they tell where the carbon monoxide was coming from?
It was in a mining site. Mining site.
Okay.
Yes, sir.
Because I know that where there is incomplete combustion, okay, incomplete combustion will produce carbon monoxide. That is why you see that in the exhaust of our vehicles, that black smoke that comes out is as a result of
Yes.
incomplete combustion. So if there is incomplete combustion, the release of carbon monoxide is very, very high, and it's very poisonous. It can kill in minutes. It can kill in minutes if you get in contact with it. Yes. So I don't know where, I can't really fathom where the carbon monoxide was coming from, except if we are able to understand the source where the carbon monoxide was being released from, then that will help us to look at some of the ways that we can prevent it. Or I don't just, I have not had the news, but maybe I will try and check up and then see. But maybe if there is someone here who has a better understanding of the story and how it happened, that will also help us. I can see many other hands, so let's give more hands and see. Okay.
Okay.
Okay, Wange.
Good morning, Prof.
Good morning, Wange. Good morning.
Thank you once again for the wonderful lectures. That your service delivery is top notch. I would like to contribute to the news, the sad news that we just received from one of our colleagues in the House.
That's fine.
Yes. When at the same time, why I'm trying to explain, she will have to give us certain input, because first of all, we have to ascertain the nature of the miming that is going there. What is the nature of the miming? We need to know.
She may not know, because I think the details,
did the miming has a cave and all that. But all the same, she mentioned carbon monoxide. Carbon monoxide, most mining sites comes from chemical reactions that is taking place on underground. It could be as a result of petrification processes, or it will come as a result of the mining procedure that is being used there, chemicals that are being used, especially in the extraction of the mining element or mining this thing that is the target. So if so, carbon monoxide is very, very dangerous. What carbon monoxide does is that it goes into your body through the lungs. You inhale it.
Yes.
And it goes there through your air bags, alveoli. And during gas exchange, it attaches itself with the oxygen, with the hemoglobin that is responsible to take oxygen and distribute it in your body system. It goes there and attach itself and use up the oxygen to oxidize itself to carbon dioxide. So as a result of that, in summary, it is depriving your body of the oxygen that your body should have used during metabolic processes to what? To generate energy for your living. So once that is done, your body is deprived of energy. And the first thing that happens to you is that once your brain cells cannot receive energy, you go into coma. And if there is no medical, immediate medical attention given to you, from coma you slide into death. So this is another danger that is there. Then the other one is methane. Most mining activities associated with caves comes with a high volume of methane, which you know that is a gas. And methane in the same way acts like carbon monoxide. Where you see methane, you will not see oxygen. You will see little or no oxygen. And that place that is full of methane gas, no human being, especially macroorganisms, can actually
Exist
survive
there.
in such environment. So as a result of that, there is gradual poisoning. People who are mining there become weak, and eventually they also pass out. So I think from the possible scenarios, since there are you did not give us certain data to analyze and get to the culprit, because I don't know whether officially an investigation was carried out and it was determined by expert that is actually carbon monoxide gas that was the culprit there. We don't know. But my analysis is based on the assumption that the carbon monoxide that you mentioned that was the culprit is what I'm using for this analysis. Thank you.
Welcome. Thank you very much for. Yeah, that's okay. I think he has made a valid point. We can also wait and see the next line of action, because it just happened yesterday, and we don't expect that the investigation will be completed by now. So we'll follow it up and see what really happened in that place. Thank you. Kalu. Hello, Kalu. Abikula.
Yes, Kula, yes. Good morning, Prof.
Yeah, please, can you speak?
Yes, Prof. What you just explained concerning the death toll at the mining site.
That's
Yes,
okay.
yes. Which I heard the news today. So what has happened? The government has ordered that they should close the place. That they'll bring experts to determine the cause of death and possibly carry out some of the procedures they have to carry, that the place will be safe for humans to return. So it's closed currently. So I listened to the news.
So now,
thank you,
I don't
Prof.
know how did they know that it was carbon monoxide? Well, we may not have answers
No,
to such questions now.
From the news I heard, they did not specify though. So it's when the investigation is carried out that yes.
Right.
So, thank you, Prof.
It's all right. You're welcome. Isaac.
Good morning, Prof. Sir, I just want to share. Yes, sir. I just want to share an experience I had when I was staying in Garaku in Nasarawa State, precisely.
That's okay.
You know, we have two types of mining: the open mining, where the whole area the mineral is found is excavated. We also have closed system of mining, where the miners dig a hole like a well, and when they enter inside, they go and expand it so that the labor and the energy it will take them to excavate the whole area is reduced. So when they enter into the hole, they go and expand it, and then it looks as if there's a very big hole inside, but the entrance is just narrow for them to enter, because some of these minerals are found deep into the ground.
Yes.
So where I saw people mining, doing the closed system of mining, you know, they use an instrument to be excavating the inside of the ground so that they will be locating the minerals they are looking for. So many times they use generators. Many times they use generator and connect their excavating machineries, instruments that
Machinery.
they are using
Yes.
inside. So I'm assuming that maybe in the course of using a generator, it's just an assumption, they kept it close to the entrance of the place, and maybe the exhaust
Mm.
from the generator was going
The-
inside rather than in an
yes.
open place where the exhaust will spread over and get diffused into the air. So
That's
as
the
a
thing.
result, they inhale a lot of the carbon monoxide. And like one
Mm.
of the colleagues said, uh, when when humans or animals inhale much of the carbon monoxide, it has high affinity to what's it called, hemoglobin, which
Hemoglobin.
transport oxygen.
Yes.
And 20%, 25% of the oxygen or of blood circulating the body system goes to the brain.
Mm.
So when that happens, much of the carbon monoxide has affinity to hemoglobin, and when it attaches to hemoglobin, it now
Mm.
extracts the little oxygen that the
Oxygen.
hemoglobin is carrying to supply to
Mm.
the brain. So
Yeah.
in that case, it brings somebody into coma, and when
Mm.
there is no resuscitation, it leads
Mm.
to death. So I'm
Death. Mm.
assuming that's the scenario that took place there. It's
That's
just an
okay. That is
assumption, sir.
another. Yeah, that is another possibility. That's another possibility. Yeah. Thank you very much.
Going.
Thank you. Dugeri,
Yeah, good morning,
Du-
Prof.
Du-
Once again,
good morning, Dugeri.
good morning, class. My issue is about the scenario we're just discussing now. You said one of our colleagues here said the company has been closed by government, and they are looking for experts to investigate what is the cause of the 7% that are dead, whether there is a release of the carbon monoxide, as some of us are saying. My concern is really who are the experts that are supposed to investigate in this issue now, the professionals involved. Thank you, sir.
Okay, the professionals will be somebody like you.
Hello? Hello, Prof. There's no sound here.
You know, environment. Uh, hello, can you hear me? Hello, Dugeri, can you hear me?
We can hear you, sir.
Right. So I am saying that to cut the whole story short, they are going to bring different professionals, ranging from scientists, environmental scientists, psychologists will be there too, medical personnel will be there too, toxicologists will be there too, and
Pathologist.
he said pathologists will be there too. So a host of professionals are going to be dragged to site to carry out that so that I also, hello, hello. Hello?
We can hear you, sir, but the call ended.
Okay. So I am saying that if you know anyone who can include me on the team, I'll be very happy to be on the team.
Okay, sir.
Right. I think we can continue. Dugari, is your question answered? Hello? Is Dugari with us? So these are the factors that determine adverse effect. You have what is called intrinsic toxicity, dose, exposure conditions, response of host. I told you that when a chemical or a toxicant is delivered onto the target molecule or target organ, after delivery, there is a reaction. After a reaction, there is injury, then repair or disrepair, as the case may be. So you may have a chemical affecting a particular organism in a different way compared to another, depending on a number of factors. Or these effects that these chemicals cause are dependent on a number of factors. Hello, are you hearing me? Are you with me? Are you with me?
Yes, sir. Yes,
right.
Sir.
Right. So you have intrinsic toxicity, you have dose, exposure conditions, response of the host. Like response of the host, if the host is strong enough to resist, then the effect might be minimal, like I mentioned before. If the exposure conditions are favorable or are in such a way that the chemical can, triumph or carry out its action, then the effect will be felt. But if the conditions are not, for instance, there are some that would cause more damage at higher temperature when the temperature of the environment is high. There are some that operate better at low temperature and so on and so forth. And if there is a situation where a particular chemical finds itself in an environment that is very high in temperature, and that condition suits it, then you should expect that the adverse effect will be felt compared to when the condition is not. And then the dose, if the dose is high, we should expect that we should have a higher, toxicity. And then the intrinsic toxicity has to do with something that is inbuilt. It's inbuilt. If it is in the nature of the organism to allow for such effect, then it will happen. It has to do with the nature, so to speak, the nature, kind of. Let's look at, so intrinsic chemical, nature. Intrinsic toxicity has to do with the nature. So here, it has to do with some properties like the molecular structure, okay? The molecular structure of the chemical, the kind of functional groups that are attached or are found in that chemical. I told you the other time that if you have a chemical that has a lot of chlorine, it will take time before it will be broken down, so to speak. But if you have the one that has less chlorine atoms, it will be easier for it to be broken down. But mind you, that chlorine is very toxic when you find it attached in any molecule. I know what chlorine can do, from hydrogen chloride, so to speak. And then there are some that are naturally soluble, okay? And there are some that volatilize very easily. There are some that are stable under light, in the presence of light, or they are not stable in the presence of light, or when they mix with water. So it has to do with the nature of the chemical itself, and then the reactivity. If it's a type that reacts very fast or slowly, then the effect will also be felt accordingly. Then the density in gases, liquid vapor pressure, solid crystal structure, and size and shape. So all of these fall under intrinsic toxicity. It has to do with the nature, inherent property, okay, or inherent characteristics. As we are here, we all have inherent, characters that cannot be changed, no matter what we do. They are part of us. So that is that. Now, there are some misunderstandings about what we refer to as these chemicals or substances that cause injury or affect us. The misunderstanding is that, but we'll clear them here. Some believe that natural products are safe. Somebody will say, it is aloe vera that I use. So aloe vera is a natural material, or it's aloe vera gel that I use. I use organic materials only. I don't use synthetic. So it is a kind of a misunderstanding. In as much as they are natural, they are not completely safe. They are not. They have their own negative effect. Synthetic agents, some will say synthetic agents are not toxic agents because they are produced in the lab or something. No. Pure substance plus impurity can also, pure substance is pure substance plus impurity. Yeah, pure substance, a complex, pure substance, a complex mixture. So these are some of the misunderstanding. You don't just say that because this material appear to be pure, or is said to be pure, it does not mean that it will not have its own effect, and so on and so forth. So we have looked at intrinsic, and then we're looking at the second factor, that is dose. So dose is the amount of a substance administered at one time. If you go to the hospital, they usually give drug for a particular ailment, and they always tell you that you should go and take the dosage. You should take 2 in the morning, 2 in the evening, 2 in the afternoon, something like that. That's what we're referring to as dose. So the amount of substance that is administered, okay, at a time or at one time is referred to as the dose. And the dosage depending on how high or low it is, it will affect human health, or it will have an effect or adverse effect. And let me also say that it is not necessary that one will be affected if the dosage is high. There are some cases where even at very low dosage or dosages, you discover that adverse effects are seen. So it is not completely true that higher dosages will produce higher adverse effect. No, in some cases, like in the case of cancer-causing chemicals, you see that we had an exception where we're discussing about chemicals that cause some of these effects. We say that at any level at all, we don't play with such chemicals, because at very minor or minute level, they will be able to induce cancer or any other effect, as the case may be. Hello, are you with me? Hello?
We are with you, absolutely, sir.
All right. So we have different types of doses. We have different types of doses. We have, yeah. Okay. Somebody is saying that network. Okay. So yes, okay. 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 Right. Okay, I'm just going through the messages. If there is anything I need to react to. So we have types of doses. You have exposure dose. This one is amount of xenobiotic encountered in the environment. Exposure dose is the one that you find in the environment. Yeah, you get in contact with in the environment. For instance, if you are driving to Boko, you get around Dangote cement factory, you may be exposed. Not you may, you get exposed to the products, okay, of cement, okay, dust, get exposed. So that is a kind of an exposure dose. That's why you get exposed in the environment generally, or the one that you are being exposed to in your house, okay, or on the road, or in the market, and so on and so forth. And then you have the absorbed dose. The absorbed dose is the actual amount of the exposed dose that enters the body. Okay, you may be exposed to a certain quantity of it, but not all of it will get into the body. Like when we're trying to differentiate between bioavailability of a substance and bioaccessibility. So the exposure dose can be likened to how much that is available in the environment, okay, that you got in contact with, and then absorb dose, that's bioavailability, right? Bioaccessibility is what is available, okay? That's in the case of exposure dose. And we can liken absorb dose as the one that has entered, the system or the blood system, so to speak. So the absorbed dose is the actual amount of the exposed dose that enters the body. So you may be exposed to, let's say, 50 milligram per liter of a particular chemical, but maybe only 5 out of the 50 that will get absorbed into the body. So that is what we refer to as absorbed dose. Then you have the administered dose. Administered dose, like when you are injected, okay, in the hospital with a particular drug, so to speak. They usually measure a particular amount and administer, okay? Or you want to do a study to understand the behavior of maybe rabbit and rat, okay? Or response of rabbit and rat, where you administer a particular dosage, a known dosage, okay? A known quantity of the chemical, okay? Then you have the total dose. The total dose is the sum of all the individual doses. So these are the types of doses that we have. Any question at this point or contribution? Hello? I'm sure if I ask you to speak on factors that determine adverse effect, or I mention a few of them and I ask you to explain, you'll be able to do that. Or I said, what do you mean by the following? Or define the following. Exposure dose, absorb dose, administered dose, total dose. You'll be able to tell me what they mean. Is it not so?
How can it?
Right. Chicken. So we mentioned something when we started discussing toxicology, when we're looking at definition of terms. We talked about dose response relationship, and that has come up here again.
Hello, Prof. Good
Yes.
morning, sir.
Morning.
Yeah, good morning. Thank you so much for the lectures. I just have a little question to ask. Please, maybe you can just give us example of this total dose you're talking about. Yes, under the type of doses. You gave us, you say total dose is sum of all the individual doses. Can we just get example of it, sir? Thank you.
If you add from up to down,
okay,
what will you get? You get a total,
okay,
is it not so?
Okay, sir.
Is it not?
Yes, sir.
It's just like you are adding the various individual doses together.
Okay, that is exposure plus absorb
Yes.
plus
Yeah.
administer all together. Is all right. Thank you so much.
Thank you very much. Right. So the dose response relationship, somebody wants to talk.
Hello,
Yes.
good morning, sir. Okay, good morning, sir. Hello, good morning. Can you hear me? Okay, so I want to ask, how can you measure the amount of the total dose in the body system? Hello?
Yes, yes.
Okay.
How can you measure it?
Yes, sir. How can you measure the amount of the total dose? Or how can you determine them in the body?
Anybody with idea shall not as much as the one teaching. I also want to hear from you, some of you who have practical experience, participants. Hello? How can you measure total dose? Hello? Yes, George.
Hello,
Yes,
sir.
George. Yes,
Hello,
go
sir.
ahead.
Hello,
Yes,
class.
yes.
I am not too conversant with this field, but looking at the table in front of me here, I can see that if someone is exposed to a particular dose, you can actually calculate the amount that has been administered to the person. So when you know the amount that has been administered to the person, then you can now calculate the amount that actually has been absorbed in the body using the
Yes.
particular media that are used to determine the amount that is exposed, the amount that actually went into the body, and then the total that was actually administered. So you can now do this computation and then know the total dose that actually went into the body. Thank you very much.
Yeah. Well done. Thank you very much. Some of these things, in as much as we, okay, there's another person. Yes, Nelson. Nelson, can you speak? Hello, Nelson, can you speak? Hello, Nelson, can you speak? Hello, Nelson, are you there? Okay. Hello, Nelson. Is it Julius?
Yes, Julius is
Julius,
Julius is
please.
active. Yes, good
Can you
afternoon,
speak?
bro.
Good morning.
Yeah, good morning. Sorry, good morning, dear colleagues. So, this concept of dose is, I would relate it especially to the lines of, how will I put it, of detoxification reaction that you gave us. That is introduction of the toxin, right, or the substance, right, and then
Yes,
reaction.
yes.
After that, then reaction. After reaction, then we have
Injury.
injury, yes, damages,
Yeah.
and whether we're repairing or it is a disrepair. So the same thing. So when we talk about total dose, we're talking about the three. That is exposure dose, plus absorbed dose, then plus administered dose, right? All together, that gives us the sum of the total. Then how can we determine it in the system? Like for the exposure dose, amount of xenobiotic encountered in the environment. For example, from the flaring, we talked about Dangote, right? When you're going to Boko, right? So that can be measured by using several sophisticated gadgets. There is this gadget that measures the amount of some gases in the atmosphere. They call them, is it ray multimeters, right? They tell you the degree of carbon monoxide in the atmosphere and all that in their percentages or in their number. So you see, that is a device that will tell you that in terms of let's say introduction of the substance into an environment which is the organism, for now maybe air, right? So let's come down to absorbed dose. The absorbed dose is the actual amount of the exposed dose that enters the body. Now, relating this to the environment is still the same thing. It will tell you the total amount, right? In figure, that's those devices. They will tell you the total amount. If it is human body, I think maybe the doctors can say that better because they will tell you the amount of toxication or intake that the patient will have. If they can, they have device to do that. But for the environment, I'm sure there are devices that will tell you that when it comes to the actual amount of the exposed dose that enters the body can either be human body or the environment, mind you, or the environmental media, right? Then when you talk about the administered dose, we are talking about the quantity administered. This one is usually what telling you what the number that this one is initiated, understand, maybe by you injecting it means maybe you releasing it, you understand, at this quantity, at this amount, it is intentional. So you have administered the quantity. Maybe let's say you are releasing how will I put it now, let's say you are releasing some certain percentages of of particulate matter in part per million, you understand, you are introducing it deliberately into an environment. Maybe your plant's capacity can release so and so in parts per million, right? And you know that this is what it releases. So that one is intentionally what introducing it. So the sum total of everything, whether to a body of human being or to the environment, right? Whichever one it falls, gives you the total dose of both the exposure, the absorb, and the administers. That's what I have to say. Thank you, Prof.
Okay. Yeah. Okay, there's another hand up. Yes. Yes, Wange?
Oh, thank you, Prof.
Hello?
Once again.
Yes.
I think, in my own opinion,
Yes.
when the total dose is a summation of all the types of dosage that that particular host or individual has come in contact with. And
Yes.
if we are to determine the amount of dosage in a particular host or body, I understand that there are different types of complex techniques that are available, such as
Yes.
spectrometry and other techniques that we know. For the sake of time, I won't be mentioning them all. We have gas chromatography. You take a sample. If an individual is exposed, you take a sample of that and the blood, and you subject it to these techniques, and they will be able to analyze that particular exposure that you are the body has been exposed to, be it chlorine, be it any chemical substance. I think these techniques are available, including nano technology in recent time. They are trying to use, they will bombard you with certain nanoparticles. They will go into your circulatory system. I'm talking about the human body, and are able to determine certain chemical compounds like radioactive elements, like chlorine, like iodine, and all that. So I think that's my own little contribution for that, in ways of techniques of determining the total dosage in a host or
Biomarkers,
body.
so
Thank
on
you.
and so forth.
Yes,
Hello, Wange, are you done?
biomarkers. Thank you. I'm done. Thank you.
Right. Thank you very much for your various contributions. Just like for those who have spoken, have said, these things are not just done overnight. They are done with sophisticated equipment or instrument, and has to do with collection of samples and so on and so forth. Okay, so in measuring total dose, for instance, in the human body, that can be done through a number of techniques, just like Wange mentioned. It can be done through the use of biomarkers in blood. It can be done in urine or tissues. It can also be done through imaging techniques by use of, say, X-ray or CT scans. That can be done, and it can also be done through analysis of this biological samples and so on and so forth. So it can be done through the use of some of these equipments that are, designed even specifically to measure such chemicals. Okay. Hello. 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 Right.
We
So
are with you, sir.
I'm sure. Okay. So let's continue. We are looking at Yes, yes. Somebody is asking whether the immune status, yes, now can be considered as a factor that determines toxicity. Yes, now. If you have a very poor immunity, okay, then you expect higher toxicity level than where you have a higher immunity. So yes, I can say yes to that. So the dose-response relationship is a fundamental and essential concept in the study of toxins. What this does actually is it correlates exposures and the spectrum of induced effects. Now we're told that generally, like I said before, the higher the dose, the more severe the response, but that is generally. So the dose-response relationship is based on observed data. So these things, not that it is the way we are saying it here. It involves experiments. It involves experiments. So the dose-response relationship is based on observed data from experimental animal or human clinical or cell studies. Okay, we are going to that. You understand better. I even mentioned it yesterday. I said, for instance, if you want to study the effect of a particular chemical in an organism or animal, for instance, maybe the chemical you are introducing into the system of that organism or animal is the one that induces diabetes. Okay? So what you do is to prepare different concentrations of your toxicant, okay, at different concentrations, maybe in 5 places, usually 5 different concentrations, and then you administer each of it to the animal. It could be rabbit, it could be rat, and then you begin to measure how much of the diabetes is induced at each level of administration. So you are going to have data for the diabetes, okay? You're going to have already the concentrations that you are using, okay, to induce the animal. So after you are done with the experiment, you now take the concentrations and plot. And the diabetes values too, you plot them. And then you're going to get a curve, or you're going to get a line, okay, that I'm going to show you shortly. That is what we refer to as dose-response relationship. Now, at 0 milligram per liter of the chemical, what was the corresponding level of diabetes in the blood of that animal? You mark it, right? At 0, you expect that nothing was administered. So there will be no change. Okay? And then you move to maybe 5 milligrams per liter. You administer 5 milligrams per liter. When you administered 5 milligrams per liter, how much of the diabetes was recorded? Okay? When you do that up to 5 different levels, you plot the values together, and then you get a graph. So that graph will give you a number of information that we are going to look at shortly. So you do this through experiment. Okay, knowledge of the dose-response relationship, knowledge. What are we taking home from the dose-response relationship concept? It establishes causality. It establishes causality that the chemical has, in fact, induced the observed effect. Establishes causality that the chemical has, in fact, induced the observed effect. It establishes the lowest dose where an induced effect occurs. That is the threshold effect. We mentioned that. It also determines the rate at which injury builds up. That is a slope for the dose response. We'll look at it shortly. So first, it tells you how much of the population, for instance, will be affected by administration of that chemical or toxicant. And it also tells you the rate at which the injury builds up. Mind you, you're going to have the threshold, and then after threshold, injury is being observed. At what point are you going to observe injury? Will the injury continue to be, or is going to stop at some point? Maybe when you get to the maximum level of administration, something like that. And then it determines the rate at which injury builds up. We have said that. Right. Hello, everyone. Hello. Is everyone there? Are you with me?
Yes, sir. We're with you, sir.
Now, can you see the diagrams on the screen?
Yes, sir. We can see them. Yes, Prof.
Curve. Those on the left. What is on the y-axis?
We can hear you, sir.
Can you hear me now?
Yes.
Now, the question is, you can see the graphs on the screen very clearly. Yes. Now I'm asking, what is on the y-axis? The y-axis is the perpendicular line. I want you, any of you should read it. I want you to read, because this is not a practical class. This is not face-to-face. So I want you to be the one to tell me what you are seeing. Yes, George. Hello, George. Hello, George. George, can you speak?
Hello, sir.
Yes, please.
It is the response percentage. The response to the dose in percentage.
Thank you. Response in percentage. And then on the x-axis, that is the horizontal line, you have dose, right?
Yes, sir.
And the dose is in milligrams. So you can now see that 5 milligrams, 10 milligrams, 15 milligrams, 20 milligrams, 25 milligrams, 30 milligrams, 35 milligrams were administered. Okay? And the response was recorded in percentage. That is 0 to 100. Now, when you plot those values, or when those values were plotted, a certain information or a number of information can be deduced from here. Now, look at the first one. The first information you are going to get from this curve, this dose response curve, is a threshold. Okay? Look at the threshold is at what dosage? At about 10 dosage. Or 10, yes, 10 dosage. Can you see that? Are you following me? Hello? Hello?
Sir, we are following, sir.
Okay. So for those of you who can answer, if I ask, just answer so that I'll be convinced. So if you look at here, at 10 milligram, there was no observable change. There was no shift at all, nothing. It is still flat. There's no observable reaction, kind of. So you can see that at 10 milligram, nothing happened. There is no response. It is 0. The response is 0. It means nothing happened. Now, if you move to the next one, by the time 20 milligrams were administered, at the time 20 milligrams were administered, we got 50%. I'm going to explain something again. Don't just follow me. You got 50% here. Okay? And that 50% is marked LD50. LD50. Who can tell me what LD means? Hello? Who can tell me what LD means? What is LD? Hello?
Imoto, your hand is up.
Yes.
Okay, thank you. LD means letter dose.
Letter what? Dose.
Letter dose. LETHL.
Thank you. Letter dose. Letter dose.
Let me
Just
write
stop.
it.
So no, that's fine. That's okay. If you like, you can write it for others who don't know. You can write letter dose. Okay. Now come to the third one. The third one, the last one. You can see that we said that dosage which is administered that leads to no response is known as what? No observable blah 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 blah, right? I'm forgetting the term myself. No observable something. Let me check that abbreviation again quickly. Let me check that abbreviation quickly. No observable adverse effect. This is no observable adverse effect level. Hello? Hello?
Well, with you, sir.
That is no observable adverse effect what? Level. At that dosage, no response was registered. It was 0. Look at the 10. Go back to the 0 at the base. Nothing shifted. You can't see any rise at that point. Okay? If you come to the second point, this one is known as the lowest observable adverse effect level. Lowest observable adverse effect level. So by the time you get to 50%, that is where you have LD50. Now, let me tell you what is happening here very quickly. This is a toxicological studies that involves the administration of that chemical, whatever chemical in milligrams, maybe to a group or to a population of organisms. Okay? And it is expected that after administering this chemical, the study wanted to know how much of the organisms will be killed by that chemical. So you discover that at 10 milligram application, no organism was killed. 0% of it was killed because there is no observable change here. There is no observable adverse effect at that point. So we refer to that as threshold. Now, if you move to the second one, by the time 20 milligrams were administered to a population of that organisms, 50% of the organisms were killed. That is the implication of what you are seeing here. 20 milligram, by the time 20 milligram was introduced, 50% of it, of the organisms of the population died there. LD50, meaning that is the concentration or the amount that is responsible for the killing of 50% of the population. That is what you mean by LD50. It means that 50% of the organisms were killed at 20 milligram administration of the drug or of the chemical. Do you understand? That is leather dose. Leather means death, and dose is 20. So at 20 milligram dose, 50% of the organisms died, or the population of the organisms died. Okay. That is what we have. That's why it is called LD50. That is why you're seeing 50 there. So 20 milligram is the LD, is a ladder dose. 50% of the population died after you administered 20 milligram of the chemical. Making noise there now. Hello? Hello? Hello, are you there? No hearing them. Okay. Okay. Response. 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 Yes. Yes. Okay. Muted. That is okay. That dose is okay. No observable reaction. That dose amount of substance required to cause death. No observable adverse effect level. No observable adverse effect. Right, that's fine. Hello. Hello, guys. Are you with me?
We are with you, sir.
Right. So if I tell you to explain what you mean by LD50, you'll be able to tell me, right? In the exams.
Yes, sir.
LD50 is that dose or is the amount of toxicant that is capable of killing 50% of the population in which the chemical is administered to. All right? So you can see that from here you can get a number of how do you call it, information. Okay, like here, if you get to 15, you can extrapolate back to the percentage or the response and know what percentage of the organisms were killed. At 25, you can also extrapolate, like that. And that is the kind of information you get from this dose response curve. So if you come here, you see at 10, no observable adverse effect level. If you move up, this one is the lowest, and then this should be about the highest, because by the time you are getting to the top, the curve is becoming flat, meaning that it does not matter how much of it you apply, it will not change anything. It will just continue to be flat, because by that time, maybe every of the organisms is dead. So you will not observe any change again. So that curve will continue to go, okay, flat like that. So that is the kind of information we get from dose response relationship. So the dose response curve normally takes the form of a sigmoid curve. It's just a description. That's a shape. That's how you describe that shape. It conforms to a smooth curve as close as possible to the individual data points. For most effects, small doses are not toxic, as you can see in the graph, that the first one, up to 10 milligram, there was no observable change, and it appears that that concentration was not toxic to that organism, so to speak. So the point at which toxicity first appears is known as the threshold dose level. Okay, we have said that before. So you can see that from the graph, from that point, the curve increases with higher dose levels. In the hypothetical curve above, no toxicity occurs at 10 milligrams, whereas at 35 milligrams, 100% of the individual experience toxic effects. So that is the explanation of what we have just looked at. Okay, at 10 milligram, no observable threshold. You have threshold, right? At 10 here, no observable change. But when you get to 35, almost all of it is gone. That is why you have the flat top. Okay. So the point at which toxicity first appears is known as the threshold dose level. From that point, the curve increases with higher dose levels. As you can see in the hypothetical curve, no toxicity occurs at 10 milligram, whereas at 35 milligram, 100% of the individuals experience toxic effects. So, right. Now, we're looking at those estimates of toxic effects now. It's what we have discussed already, but I'll still point it out here. So, it does not mean that it is 20 milligram of the chemical that will kill 50% of the population in all cases. So LD50 can be 5 milligram, it can be 2 milligram, it can be 50 milligram, it can be 35 milligram, depending on the toxicity of the chemical and the response of the organisms or the target material. All right. So those response curves are used to derive dose estimates of chemical substances. A common dose estimate for acute toxicity is the LD50. That is leather dose, 50%. This is a statistically derived dose at which 50% of the individuals will be expected to die. Okay? The figure illustrates how an LD50 of 20 milligram is derived. So other dose estimates may be used. LD0 represents the dose at which no individuals are expected to die. LD0. Okay? This is just below the threshold. It's below the threshold for lethality. LD10 refers to the dose at which 10% of the individuals will die. Do you understand? Hello? Hello? Are you following me?
Yes, sir. We are following you, sir.
Thank you. So no observed adverse effect level, we have looked at that. Low observed adverse effect level, we have looked at that. They are the actual data points from human, clinical, or experimental animal studies. Sometimes the terms no observable effect level and low may also be found in the literature as NOELS or LOELs. They do not necessarily imply toxic or harmful effects and may be used to describe beneficial effects too of chemicals as well. Because where there is no effect, then it means that chemical could be beneficial, so to speak, and have great importance in the conduct of risk assessments. Now, we have looked at this. No, we have not, but I think these are also familiar routes. Just trying to tell us the routes through which these chemicals can pass through before affecting us. So you have exposure conditions, you have routes of exposure, frequency, and duration. So the route in which the chemical passes through to affect human health, for instance, is also very important. The frequency of exposure is also another factor, and duration of exposure. There are certain chemicals that when you are exposed to them for a very long time, they cause adverse effect, compared to when you are exposed, seldomly, kind of. And then you have mixed exposures, okay? Being exposed to different kinds of, to different you are being exposed to different routes, so to speak, different conditions. All right, environmental circumstances is another factor. Maybe where the temperature of the environment is high or low, and maybe you can observe more effect at higher temperature than when the temperature is low, or when the environment is humid, or when the environment is dry, and so on and so forth. Right? Then the routes of exposure include oral, that is through the mouth, inhalation through the nostrils, then derma through the skin, and then parentera. Parentera. Which one is parentera now? Which one is parentera? Hello? Which one is parentera as exposure route? Parentera as exposure route. Which one is parentera? Parentera. Parentera as an exposure route. Okay, that is through injections. Okay, through injections. Parentera is through injections, and so parentera refers to administration or exposure through routes other than the digestive tract. Okay, like IV. It's okay. So these are the exposure routes, and then the sources. So the exposure routes and the sources. We are here. We are here, sir. We are here. Okay. Yeah. Okay. Cuts and wounds. Okay. Someone say through cuts and wounds. Okay. Parentera could be digestive tract, vein, wound, skin. That's okay. Gastrointestinal tract, typically injection, infusion into the body. That's all right. That's great. Thank you. Exposure route sources, oral exposure, water, soil pollutants, contamination of food. When you eat any food that is contaminated with any chemical, or you drink a water that is contaminated through the mouth, okay, or by hand-to-mouth behavior of children, that is oral, or hand hygiene. Maybe some of you are very fond of putting hand in your mouth, and so on and so forth, so that is oral. Inhalation through smoking, indoor air pollution, and so on and so forth. Derma is through occupational agents like solvents. We are working in an environment that produces solvent, pesticides, cosmetics, some water pollutant. Is very likely that you may get in contact with them through your skin, and they may absorb into your body through the skin too. So parentera, we have said what parentera is. Factors influencing toxic effects. We have looked at that. These are just re-emphasizing them. Then we have a number of effects. We have systemic toxic effects. Toxic effects are generally categorized according to the site of the toxic effect. Sometimes the effect may occur at only one site. So this site is referred to as specific target organ. specific target organ. So if it affects only one site, then it's known as specific target organ. In other cases, toxic effect may occur at multiple sites. This is referred to as systemic toxicity. So if it happens at different sites, then it's referred to as systemic toxicity. If it is at one site, then it's what? Specific target organ. So you have types of systemic toxicity that is happening in multiple. You have acute, subchronic, chronic, carcinogenicity, developmental toxicity, genetic toxicity, so on. Acute toxicity occurs almost immediately, within hours or days after an exposure. So if you are exposed to a chemical or a toxicant, and it manifests, okay? Manifests within hours or days, then we refer to that as acute toxicity. They are capable of causing injury within hours or days. That's acute toxicity. Okay, so an acute exposure is usually a single dose or a series of doses received within 24 hours period. Death is a major concern in cases of acute exposures. So it can happen very, very, very fast and quickly, which is dangerous. Then the other definitions are there. Subchronic toxicity. This is repeated exposure. Okay, this one can become affected if you are exposed. Results from repeated exposure, okay, for several weeks or months. So this has to do with repeated exposure, okay? This is common human exposure pattern for some pharmaceuticals. An environmental example are injection of blood thinners for several weeks as a treatment for, thrombosis can cause internal bleeding. And maybe in your workplace, you are being exposed to a particular chemical, all the time in your workplace. And so chronic has to do with, it represents cumulative damage to specific organ. It takes time. It takes time before you experience the effect. Oh, time is going. It takes time before you experience effect. As chronic toxicity, it takes a number of time. Subchronic is repeated. Acute is one time. There you see the effect almost immediately, right? We stop there. We are almost done, but we'll stop there and then see how we can. I don't know, but I'm suspecting that. Hello, class. Hello. Hello. Hello, everyone here. Hello. Hello. Right. We will stop here. We will stop here. We will stop here. Okay. Right. So we'll stop here. But I am suspecting that we may not meet in the afternoon. I am suspecting that we may not meet in the afternoon because I have a meeting that I need to attend, and that meeting may drag beyond 1 o'clock. So if I'm able to conclude the meeting before 1 or by 1 o'clock, then we'll meet. If not, we will continue tomorrow morning and round up tomorrow. Okay? Is that accepted? I think you can unmute yourselves. Anybody, you can unmute everybody. Possibly unmute everybody, please. Or can you unmute yourselves? We have 3 minutes to go. No. I can't teach in the evening. Okay. Okay. You can't meet in the evening. I need to give family time now. So if we can't meet in the afternoon, we'll continue tomorrow morning, please. Thank you very much. See you later or see you tomorrow. Bye-bye.